Continuing with the Thermo review, this is part 2. We just done number 10 and found out that because this was a negative answer, it was going to be a reaction that will occur. This right here, number 11, reactions tend to favor negative enthalpies, which I mentioned in the last video, and positive entropies. The reason is because Mother Nature is lazy and crazy. Lazy, meaning we want energy to go down, so lowering the delta H, or making it negative. And crazy, we want more entropy, so we want a positive delta S. And let me actually tidy this up a little bit. I'm going to rewrite this section. I don't want the delta right there. I think it'd be better to say lower the enthalpy, which is a negative delta H. That's a better way to say it. Now, sometimes just looking at a reaction, you can make a prediction. That's number 12. It says, given the reaction, predict the sign of delta S. So in other words, is entropy increasing or decreasing? Well, we've got 2 moles of gas here, 1 mole of gas here, and over here we only have 2 moles of gas. So 3 moles versus 2 moles, that's less chaos. Another thing you could look at is that we have 2 different chemicals. We have an H2 and an O2, and over here we only have 1 chemical. Now, the molecule is more complicated, but that's less types of things. So that's another reason that the entropy is going down. That would be a negative delta S. Number 13. You'll need to use table 8.1 because you have to look up the specific heat of iron. Ends up being this right here. This particular chart is in joules. Sometimes they're in kilojoules, so just be careful. Make sure for delta T, you do final minus initial. So final is 25, initial is 800. And just make sure everything matches up. Our grams matches, our Celsius matches, and they both get canceled, so you're left with an answer in joules. I had to fix my sig figs on this one because you should only have 3. A lot of students mess up sig figs on this. They go, oh, 25 only has 2. Well, you're right, it only has 2, but after you do this part of the problem, you now will have 3, so then your answer ends up with 3, like I have written. Now, this is a single step Q problem. So we're solving for Q, the amount of heat, and there's just one step. It was just using the Q equals MC delta T. 14 is what I call a combo Q problem. You have to do multiple Q calculations, and there's a graph that can help you with this concept, so it's worth a moment to look at this. It goes by different names, but it looks like this. This will be temperature over here. This will just be, I guess you could just say, like the different process that's happening. There's an exact phrasing for this. I don't remember it right now. And if we take something like water, this shows a temperature change. This shows no temperature change. This shows a temperature change. This shows no temperature change, and this shows another temperature change. And so the first thing to notice is that here, here, and here, those are temperature changes. And for those, you would want to use Q equals MC delta T. because delta T is temperature change. Whereas here and here, those are not temperature changes. Those are phase changes. And that ends up being a mole problem using delta H value for those particular phase changes. And let me add that. So these would be a phase change mole problem, which we will see in this example that I'll get back to. In the case of water, under normal conditions, this temperature right here would be 0 degrees Celsius, and this one up here would be 100. Based on this would be solid becoming liquid, and this would be liquid becoming gas. And you need to keep these processes separate. So you can think of the graph as having 5 sections, and each section must be solved separately. So this would be section 1, 2, 3, 4, and 5. And so if the problem wanted to be really nasty, it could have you do all 5 separately, and then you would add them together. So we'll take a look at this one here. It says to use 2 different tables, table 8.1 and 8.2, because one of these tables will have the specific heat that we need here. The other will have the delta H right here. Now, in this case, it says it's going from liquid at 34 to gas at 100. So if I go back to my graph, liquid at 34 is about, well, that's 50, so probably about here, right there. And we're going to gas at 100, which is right here. And so notice that involves both part 3 of the graph and part 4. So that's why it's going to have 2 steps in my math. The first step is if we have liquid at 34, we can raise its temperature to 100. And we do that with Q equals MC delta T. And you get 15 kilojoules. Then once we have a liquid at 100, we can now turn that to a gas at 100. This is a phase change. So this is just a mole problem. So grams to moles, and then using the delta H, every 1 mole, you have to put in this much energy. 40.7 kilojoules per mole. You end up getting this. Add the 2 together for the 2 separate processes, and you get your final answer. And again, this is a 2-step combo Q. The worst that you could see is a 5-step. It's not hard, it's just time consuming, and you have to be careful and do all the steps. Now, some people will say, oh, well, let's say I have a temperature change that I have to go for. Let's say I have a solid at negative 15, and I have to take that to a solid at 0. And then let's say I take my solid at 0 and I convert it to a liquid at 0. And then let's say I have my liquid at 0 and I go to a liquid at 45 degrees. Some people go, oh, well, the first and the third steps are both temperature changes. So I can combine those with Q equals MC delta T. And no, you can't. Don't do it, because solid water has a different specific heat than liquid water. So you must keep them separate, even though it's the same equation. Now, I mentioned this here. We recently did gas lab number 3. And in gas lab number 3, you determined this value for yourself, which is the enthalpy of vaporization for water. In other words, water going from liquid to gas. And the point of the lab wasn't really to look at this value. It was just to get us something to calculate so we could see how well we did. And of course, you had to look this up in the book and use it in your percent error. But anyway, there it is again. It was, I wanted to reference that. All right, moving along, number 15. Now we start to see Hess law. Now, a lot of people on 15 wouldn't even call this a Hess law problem. I like to say that it's an easy Hess law because you're using the concept that if you flip the reaction, you must also flip the delta H. So it says, I want the enthalpy of this reaction given here. And notice what's written right here is the reverse of a combustion reaction. This chart down here, these are all combustion enthalpy values. So notice that I am zooming in on the wrong, there we go. Notice it's specifically combustion, not formation, not some other reaction. These are just for combustion of these fuels. So here's the fuel. And of course, you would typically add water, sorry, not water, oxygen. And then you would make CO2 and water, or you would just combine things. So I'll show what that looks like. So here's the fuels, same thing. The substances are listed by name, and then they're listed by formula, which is more useful. And then notice these are the delta H's. And look at, they're all negative. That's no surprise. This is a fancy way of saying burning stuff. Burning stuff always produces heat, and that is shown by the negative enthalpy values on this chart. So it actually makes sense. When doing Hess law in first year, most teachers, including myself, we do not use the combustion chart. We usually use the heat of formation chart. And in this case, you have to do formation reactions. And I talked about that in the first video on this worksheet. That is where you make something from its elements. That will most of the time be different than combustion. Now, it's possible that a formation and a combustion happen to look the same, but most of the time they won't. They will be completely different reactions for a chemical. So I find when students are asked to do Hess law with this new chart, this heat of combustion, all of a sudden they're a little bit freaked out because they've only used the formation chart. You can use any reaction with Hess law. It doesn't matter. We just use the formation chart because it's the easier chart. So back to this problem. So what I have here is the reverse of the combustion of C3H8. So I just looked up the value in the chart right here, which was your C3H8. It's a little bit tiny and hard to see, but there's the value right there. In the chart, it's negative 2219.9 kilojoules. No surprise that it's negative, but we're doing the reverse. So I have to flip the sign, which gives me a double negative and a positive here. So you don't have to go through all the steps. You don't have to write the reactions out, flip them, add them, and all that. It's just a short one. Now, 16, I mentioned this is a tough Hess law. I don't think it's really a tough one. It's just more of a typical Hess law where you have to figure out what you have available and how are you going to get the desired reaction. So this is the desired reaction. We want C7H16 to react with oxygen to make carbon and water. In this case, it says using the table below. So you have to use what's available in these combustion reactions. When you do a Hess law problem like this, I recommend that you start out right here and just write the reactions based on the chart. So just write out what you can get from the chart. In the second step, these will be the adjusted reactions. In other words, we've adjusted them to what we think is going to work. And then this last step right here is just a proof. You're just making sure that it works. And if it all goes according to plan, you just add your numbers in the end. It's a lot of work just to add numbers, but that's the point, is to make sure that it works and to prove that it works. So since I have to use combustion reactions, what catches our attention is that's a fuel, so we can write a combustion reaction. So I've done that here. C7H16 plus O2 forming CO2 and water. That value is on the chart. If you look down at the chart on your worksheet, you will see that the value is -4811.2. Now, what's weird is that this has carbon over here. The reaction we wrote doesn't have carbon by itself. So if you look at the chart, you will also see carbon right here. So we can do the combustion of carbon. And this one looks a little different. If you try to take carbon and react it with oxygen and make CO2 and water, you run into a problem. You can't make water in this case. So this is the other typical type of combustion reaction in which you take the fuel, you still add O2, but they essentially just combine, and in this case it makes just CO2, no water. And I have that here, carbon, oxygen, making CO2, it's already balanced. And if you look up the value, it's -393.51 kilojoules. Why some of them have different precision than others, I don't know. And now at this point, all I've done in this first section is I've just written the reactions as they come from the chart. Now you have to think, what can we do to these reactions so that they will add up to the desired one in the question? Well, the first thing to notice is that my carbon is on the wrong side. I need this to be a product. So I'm going to flip the reaction, and I denote that with this little arrow. Sometimes I write the word flip. The other thing to notice is that I need 7 of these. And so in addition to flipping, I'm going to multiply it times 7. So this is just my note keeping of what I'm doing to this. Flipping and multiplying by 7. And of course, you see the result here. Flipped and multiplied by 7. So the products and reactants change sides, and everybody gets multiplied by 7. Hess law says you have to do the same thing to the delta H. So if you take -393.51, change the sign and multiply by 7, you get what I have here. +2754.7. The other and first equation that I wrote, this one was okay right at the beginning. I needed 1 C7H16 as a reactant, and I just happened to get it. So this one, I didn't do anything to it. I left it as is, and I just copied it. Same thing here, as is above. So I just copied the delta H. Now we have to prove this. So I like to put a little wiggly line through all my arrows to kind of separate. Here's my reactants on the left, all of them. Here's my products on the right. Start by canceling things because it's fun. So my 7CO2 cancels my 7CO2. When things are on opposite sides, they cancel. If they're on the same side, then they add, just like when adding equations in math. This is the only one of its kind, so I copied it down here. This is the only one of its kind. Actually, no, I take that back. I've got 11O2 on the left. I've got 7O2 on the right, so this gets canceled, but that leaves, this cancels this and leaves it as a 4O2, and so I wrote that here. This is the only one of its kind, so I kept it. This is the only one of its kind, so I kept it. And then if all went according to plan, the reaction that I have here will match what the question asked for in the beginning, and it does. So what that means is that these two values just need to be added together. In other words, if the two reactions I have written add up to the desired reaction, their enthalpies add up to the enthalpy of the desired reaction. That is what Hess law says. And that's it. So if you're given a particular chart to use, so let's say you were given a formation chart, make sure you do formation reactions. If you're given a combustion chart, like in this particular example, do combustion reactions. If you're given both charts, then you get to pick whatever is going to make sense, which means there actually might be more than one way to do it. I usually don't do that because it just leads to more chaos and confusion. I usually give a specific chart. And you'll see most of our problems will do that. They'll say using this particular chart. So make sure you do it. Don't go using other charts because you might get the same answer, but you're not practicing the skill that was intended. Now this finishes this worksheet. However, I am going to do one more video in which I want to go over something that's not on this worksheet and really does need to be added. We need to talk about this graph. It was mentioned in the first video where you have your reactants here, products here. They go through this journey of energy like that. And we need to talk about where delta H is on here. We need to talk about where activation energy is and what it is, and so on, and why it has this hill-looking shape. It really should be on this worksheet. So I'll make a separate video about that. If you don't know this concept, you must watch it. If you think you know this concept, you should watch it. And if you know this concept, watch it anyway, just to make sure.